Hi, chemistry students. It's me again, Mrs. Mitzik, and I'm here to talk about the second video in our Chapter 13 series, which will deal with gas pressure and pressure conversions as well as temperature conversions. This is going to be more of a mathematically oriented video. So here we go. So how does kinetic theory explain gas pressure? Gas pressure results from the force exerted by a gas per unit surface area of an object. If you remember, I talked about how gases move rapidly, randomly, and constantly. And because of that motion, they end up bumping into things and into one another. So gas pressure itself is a result of billions of rapidly moving particles in a gas simultaneously colliding with an object. If you're looking at a vacuum is empty space. There's nothing in there at all. No particles, no gas particles, liquid particles, solid particles. It has absolutely nothing. Since there's nothing in a vacuum, there's no pressure because there's no collisions. You have to have collisions in order to have pressure. Atmospheric pressure, though, is due to the collision of atoms and molecules in the air with objects. So if you're looking outside of your window right now, you can see the air, not really at all, but if, let's say you could, those little particles in the air would be bouncing off the trees, the leaves, the cars, the trucks, the ground. It would be bumping into that, and that creates atmospheric pressure. As you go up a mountain or you go higher in elevation, your atmospheric pressure is going to decrease because the density of the atmosphere itself decreases. There just isn't as much gas as you're moving up in elevation. If you're moving up in elevation, there's not as much in terms of gas particles. There's going to be less collisions. Therefore, you're going to have less atmospheric pressure. So how do we measure atmospheric pressure? We look at it in terms of a barometer. A barometer then is going to measure the pressure. Now, an old-time barometer, the way it worked is that you have this mercury in a cup, and it was an open container. The air pressure would push, those collisions from those particles would push on the mercury, which is a very, very dense metal that's a liquid at room temperature. If you had higher pressure, you'd have more movement, more particles pushing down on that mercury, causing then the mercury to rise, which would cause high pressure. However, if you didn't have, you'd had very little particles, then you're going to have lower pressure. So that's how it's measured by a barometer. So when you're looking at weather forecasters and they talk about low pressure systems and high pressure systems, high pressure systems are when it's really nice outside. You have lots of gas up in the atmosphere. There's, the gas, the water vapor, all those different gases, they're moving around happily, constantly, randomly moving, no big deal. When you have low pressure, what happens is you typically have cooler weather, which causes condensation. Those gas water particles come together, and so now you've got less pressure and it's a lower pressure state. And then when a low pressure meets a high, that's when you get all kinds of trouble. So, if you're looking at a low pressure system, what happens is a column of mercury, the pressure is going to fall. So when the pressure is falling, we know that we're going to have some kind of event, weather event that's not happy. So there's some equivalent measurements that we use for pressure or atmospheric pressure. We use atmospheres, which is ATM. That's a shortcut for writing atmospheres, 1 ATM. 760 mmHg, which stands for millimeters of mercury. That's how you measured it in that barometer that we'd seen earlier in this video. And then another way we can measure pressure is 101.3 kilopascals. or I remember it by thinking 101.3 kDWB. I don't know if that works for you. If you remember, standard pressure was defined as a pressure of 101.3 kPa, 1 atmosphere, or 760 mmHg. And then also standard temperature was 0 degrees Celsius. You'll need to know those things for our next unit, so it wouldn't be a bad thing for you to remember what STP stands for and what the values are for STP. So let's do some math. I can hear some of you groaning right now, but let's do some math. So you have a pressure gauge. It's going to record a pressure of 450 kilopascals. We're going to do two calculations. We're going to convert, first of all, our kilopascals to atmospheres, and then we'll do a second calculation where we're going to take the kilopascals and we'll convert to millimeters of mercury. So I've just made this in a little easier way to see it. So we're going to do two separate calculations. So the book company says it's a good idea to set up your list of knowns and unknowns. We know our pressure. We know that the pressure is 450 kilopascals. We also know some equivalents. We know that 1 atmosphere is equal to 101.3 kPa. We also know that 1 atmosphere is equal to 760 mmHg. Just like we know that 12 inches equals a foot, 1 atmosphere equals this. Just like we know 36 inches equals a yard, we can have those equivalents. You see what's going on here? So these things are great for unit conversions. What we don't know is the pressure in the atmospheres and the pressure in mmHg. So again, we're going to do two separate calculations. So this is going to be our first calculation. We're going to take our 450 kPa and we're going to get it to atmospheres. It makes sense that kPa, that's our unit we don't want, goes in the bottom. And ATM can go on the top because we know something that's equivalent between the two of those. 1 equals 101.3. Our same setup can be done here. We have 450 kPa here, so kPa goes in the bottom, but now we're going to put mmHg on the top because that's what we want. And we know our equivalent factors for mmHg and kPa are 760 mmHg for every 101.3 kPa. So here's how the math actually looks. I've got my 450 kPa. I write down the number and the unit. I always write down on the other side my ATM, what I'm looking for. This unit will go on the bottom, and I'll say, yes, I know ATM to kPa. I know there's 1 ATM for every 101.3 kPas. And then you'll just take this, divide by this to get your answer. Same thing through here. I have 450 kPa. I'd write that starting. I would put mmHg over here, and then I would make sure that my kPa unit cancels out. I know that mmHg and kPa are comparable. When you have 760 mmHg, you have 101.3 kPa. And then I would take 450 divided by 101.3 multiplied by 760, and I should get this answer. So that's how you're going to be solving. Always look at your answer to see if it makes sense. Okay, you want to make sure that if you're going from ATM to mmHg, your numbers should get bigger because it's 1 ATM to 760 mmHg. So make sure your answer makes sense. So a little review. Let's see if you remember, and I would pause the video and think this through before you start again. What is the pressure in millimeters of mercury inside of a vacuum? Well, we remember that a vacuum has no particles whatsoever. And if we don't have particles, we don't have collisions. And if we don't have collisions, well, there's no pressure. So there's no pressure. So let's look at the relationship between kinetic energy and temperature. When you heat up a substance, we all know that the particles are going to start moving faster. It would be like if I had hot plates underneath all of the chairs of the desks in my room, and I'm an evil teacher, which I am, and I turn up the heat, And you'll start writhing and wriggling around a little bit more and a little bit more as things get hotter and hotter. And pretty soon you're going to be jumping out of your seat. Same thing's true with the particles. As you heat them up, they start moving faster and faster and faster. So if you increase the kinetic energy, you increase the temperature as well as vice versa. So at any given temperature, the particles of all substances, regardless of physical state, have the same average kinetic energy. So if I have, let's say I have some solid block at 100 degrees, and I have a liquid at 100 degrees, and I have a gas at 100 degrees, all three of them have the same kinetic energy. So make sure you understand that an increase in the average kinetic energy of a particle will cause the temperature of the substance to rise. More movement, more temperature. Think about you. When you're moving around, you get hotter, don't you? As a substance cools, the particles will move more slowly. Therefore, their average kinetic energy will decrease. So increase in kinetic energy causes temperature to increase. It's a direct proportionality, a direct relationship. When we're looking at absolute zero is the temperature at which the motion of all particles theoretically ceases. Okay, you can't get any colder than that. We've been able to get kind of close, about 1 degree or 1 Kelvin, but absolute zero, that's the part at which all things cease. So let's look at the conversion, temperature conversion for this. I've got two formulas. I know that it was 0 degrees Celsius. Okay, the lowest temperature is negative 273 Celsius. 0 K is the lowest Kelvin temperature. Okay, so it makes sense I can come up with these equations. K equals the degrees Celsius plus 273. And then I could go the other way around and say my degrees Celsius equals my Kelvin temperature minus 273. So let's do the math. What is the temperature in Kelvin of a gas collected at 23.5 degrees Celsius? And this is something you're going to be doing in our next unit along with those pressure calculations. So it's really important that you know how to do it now. So I'd like you to pause this video and work out that problem before you start it up again. I'm thinking that you're pretty successful in determining that you're looking for Kelvin, so you're going to use this formula. So you've got your Kelvin temperature equals degrees Celsius. We know it's 23.5 degrees Celsius. You add 273, and shazam, you get 296.5 degrees Celsius. Okay. So let's have you try this one. What is the temperature in Celsius of a gas at 342 Kelvin? So pause the video and go ahead and solve for that. Again, I think you're very successful in knowing you have to use the degrees Celsius equals equation. You'll plug in for Kelvin 342, and then you will end up with 69 degrees Celsius as your end result. Make sure you understand that the Kelvin temperature of a substance is directly proportional to the average kinetic energy of the particles of the substance. If one of those goes up, the other one also will go up. If one goes down, the other one will also go down. So here's another question. What is the result of increasing the temperature of a gas sample? Read through these answers. Choose the one that you think is right. Pause the video, and then resume it. We know that it's an increase because we know it's a direct proportionality. That is the ending of our second video for chapter 12 or 13. Have a great day.